Thanks for giving the opportunity to talk. So this work actually it's a little bit more dated compared to what I did mostly with David, but I thought this was something different. And so this is some work that I've done in the past with Rob, Stephen, and everybody moved on from what they were before. And so it's more from the applied side of trying to understand how you can use these. And actually, a lot of questions of, emerge when you're trying from an engineer to try to apply these techniques and from a mathematician to try to use this technique. And so the problem that I'll speak, they have some commonalities in terms of the mathematics that they use. And this problem actually came from the project that I had in the past. And so one is, the problem of trying to find, to locate an agent that is moving in an environment using an uncooperative, they call it signal of opportunity. So just imagine, you go downtown in a city, you find a bunch of us around, but you don't know where they are, you don't know what is their communication power. They are not meant here to help figure out where you are. They're there for other purposes. And so the question is there a way that anyway you could leverage that infrastructure to try to find where you are? And again, you don't know where you are, you don't know what the infrastructure is, and you may have some prior information that I'll explain you in a while. Another problem that I've been working on, was more on process evasion. So Rob has done some work on process evasion using. But what we were trying to do in this project was to connect these ideas to a problem of planning in robotics for autonomy. So when you have a problem of planning, you can try to solve it as an MDP. But as trying to solve the entire decision-making process as an MDP just doesn't scale. It's impossible because the state space of a robot would be every possible position in continuum, so it's fundamental. Cannot. So typically what you try to do is to partition the problem into you take advantage of the multi-scale property of the problem. And so if you want to catch an evader, you try to have a mission level plan, which is the market decision process, which is trying to coordinate the pursuers. And then the motion planner is what is trying to do is solving local problems. Okay, we decide to go somewhere, catch the evader. Now, how am I going to get there is my problem, and it's something that I solve locally. And then, of course, the controller is what we get. And so here, what the question was, what kind of abstraction do you use at the mission level planning, which is our modification process, which helps to abstract and try to leverage this information more from a qualitative perspective. And then on the motion level planner, how do we represent this problem so that we can capture some of the properties of the vehicle, such as sensing and motion. And so the tools that we've been using is visual complex homology. I'll speak a little bit about some of these things. So when it comes from the localization, the idea here, I guess I can point. You need to press something?
The top. It's the cursor itself.
Oh, it's like all right. So you can imagine that you're downtown some city and you're moving, and so you're somewhere, you don't know where you are, and what you take is just listen to all the access points nearby you and collect that information. Then you move a little bit and you collect some information again. Here the assumption is that if I am in line of sight with the access point, I will detect it. If it is on the other side of the building, I will not detect. Now, this is a wrong assumption in general, right? Because I will listen, hear something from something that is behind the building. But whenever I say homology, just think about persistent homology. Noise, if you don't know what that means later. But for now, just let's make this simple assumption. And so it turns out that if you sample the space and you have enough of these access points, you can actually create what is called a Dowker complex, which is a complex based on relations, where the relation here is that there is a zero simplex where I took the observation. So these things are embedded, but of course I don't know where I am. It's just a list of nodes and vertices, edges, and triangles and whatnot. And so then you have two observations are linked by an edge if they had at least one of the access point in common. It will be a 2-simplex. There were 3 observations in common, and so on. And there is 2. The data complex has a dual. So you have the observation complex to the lemma complex, and this is very nice because if you have many more observation than lemma, then the lemma complex is less complex. In this case, it's the opposite, and so you can actually have this nice computational perspective, and you can use the one that has this complexity. So now, how do you connect the homology, and what is the idea here? So the idea here is that the way to imagine this practically is that I have just imagine that the buildings are pins that are fixed on a two-dimensional plane, right? And then I have a prior map that I build, which is this complex. And now it turns out that under the assumption of usability, holes will correspond to buildings, which are my pins. So just imagine that I have a piece of paper with holes, and I have this pins, and I'm trying to find how to match this paper on this pin. And if I know where I am on the piece of paper, so and that is where I use the homology in a second, but if I know where I am on this piece of paper, when I then match it on these pins, I will be able to find where I am if these pins are localized globally, right? So that's the idea. So the idea is that the buildings is where the geometry is, but I don't know where the how I am with respect to buildings, so it's just black things. And this complex has holes, which has a one-to-one correspondence with buildings. And so the idea here is that, excuse me? I don't know if I said that word, but what I mean is that the observation here, you don't know distance. You just have a list of access points that you hear when you are in the blue spot. Just imagine just a list of numbers, unique ID corresponding to it. Yes. Yes. So what is the idea then? Is that on one side, then you are collecting MAC addresses or SSID numbers. You can use the power that you receive from this access point to read out some of it. You build this observation complex or the lemma complex. You look at the Cohomology. I need a notion that is, if I just take the homology of the entire complex, I just get the number of buildings, useless to localize. I need to get something that is finer grained, which is telling me if I were somewhere here, for example, how many holes do I see, at 3 hops, 5 hops, 10 hops, right? So I can now start having a little bit more of a fine-grained information, and I use this measurement into a particle filter. So this is very engineering, right? Well, to try to figure out where I am. Now, what is interesting, if you think about the estimation theory, and so statistical signal processing, what typically you have is you have equations that tells you what is your measurement, your measurement, the variable that you want to estimate, and you have then a noise model, which is the problem now. But now everything here became topological. What is the observation model if I want to use that information through a particle filter? That is asking me, well, okay, this observation is coming in this possible way with some, Gaussian noise or something like that. How do you do that? So this requires us to topologize our measurement observation model through some similar one. I mean, there is a correspondence here, so that you can fuse. So in practice, and I don't know if this will play on this, doesn't. So, but actually, we did collect data. We went downtown the city, we collect data, and then the particle filter will try to find where the vehicle is. Obviously, it's all qualitative, so you're not going to be able to find exactly where you are. You're counting holes. So you're saying, well, how many holes do I see closer, which means how many buildings do I see close to me? And based on this information, you try to find all the spots that correlate. And so it turns out that, anyway, I can show you my computer that you see the vehicle moving around, and this is the model. This is how the complex look like under the assumption of pure visibility. This is the complex that you get from measurement that you can see is very, very noisy, extremely complicated. So we're not able to really have a fantastic match there. The other problem, I'm running out of time, was the one that I said about hierarchical planning. So the idea here was to use heaps on the top and nerve complexes in the middle. So you have a market decision process that you heard about. So the idea of finding a sequence of state and actions that go to a goal state. And what Rob showed is that if there is a global section in the sheet, then you're not able to catch the data. So the idea here is that instead of reasoning about the environment at that level, typically if you have a market decision process, what you need to do is to discretize the state, right? You create a cell, the composition of your domain, the state becomes a cell, the action is whatever action to go from cell A to cell B. You're trying to find a policy on this cell, the composition that does whatever optimization. Searching for this value function that optimizes one, and then you search. The idea was that if you take one branch of this market decision process, you can actually associate, so the base state becomes your states, and then you have actions that connect states, and you can look how the connected components of the environment changes based on the position of the person. And all you need to hear really is when the connected component change. If your action is not changing the number of connected components, it doesn't matter. You don't need to replant anything. That is really nice because then it changes a lot the complexity. Now for the lower level planning, typically what you like to do is to find a motion that, because we're trying to find an invader, which is sort of covering the space. And in this context, what came out, it's interesting to use, people tend to, again, when they think about this problem, just to restrict a one-dimensional structure, which is graphs, instead of taking complexes. But complexes are much more beautiful when you want to start taking into consideration sensing. And so if you have a sensing footprint, maybe some other one, and as long as they're complex, you can build a nerve complex. Gives us the one skeleton of that complex actually tells us what are all the that to the market decision process then becomes, you can actually collapse a bunch of states which corresponds to nodes for which the number of connected components is the same. So I only need to act at the top level when we make actions that change drastically my topology, which is the number of connected. And at the lower level, I know how to move around based on this nerve complex. So this compresses the information a lot and helps to try to solve this. And of course, bring in the sheets. Okay, why would I need to take the sheets? I mean, what I'm only capturing on top of the sheets is on the stocks is just the component, but you actually can add more complex information. A simple one there, you can have a Vader capture criteria with the one per square to catch an evader. You can start thinking about, okay, if I have constraint on my network, again, you can encode that on top of the sheet to find, when you have or not. So with that, I think I'm probably over time.
Is this real time? Is this all real time computation? Like things are happening?
Well, the last part is probably more conceptual, but this previous one, yes.
Okay. You have with it? All right, we've got one more short.